In the mid-1990s, Miranda was a 16-year-old girl in Taipei, Taiwan, working in a record store. She was good at math and physics. She just wasn't really interested in it. She was a rebel girl. She did not fit the mold. As a child, her first interest was literature. At age 12, this passion shifted to music. She listened to pop, rock, and punk, and at 16, decided to become a punk rock musician. She had dropped out of high school and left her family home. 25 years later, Dr. Miranda Cheng is an associate professor at the University of Amsterdam. She is a leading theoretical physicist, navigating the frontiers of string theory, number theory, and algebra. How did a punk musician go on to become one of the world's most promising young theoretical physicists? How does the high school dropout become one of the principal architects of a mathematical conjecture that connects different continents of science? This is the journey of award-winning theoretical physicist Dr. Miranda Cheng. Miranda Cheng was born in Taipei, Taiwan, in 1979, and her early passions weren't really in science. She remembers, "When I was a kid in Taiwan, I was way more into literature. That was my main focus. When she was about 12, she got into music, everything from pop and rock to punk. She was, by her own admission, always very good at math and physics, but wasn't really interested in it. Her relationship with formal education was difficult. And I always found school insufferable and was always trying to find a way around it. She would negotiate with teachers to avoid class or take months of sick leave while perfectly healthy. The problem was that she found the material too easy for her age. She skipped 2 years of school, but that didn't help. Her academic talents were undeniable, and she was placed in a special class for gifted science students. This move, intended to help, was a disaster. Everybody there was very competitive, and she just couldn't deal with the competition at all. The pressure of the competitive gifted program led her to a breaking point. She became depressed. At 16, she stopped attending school. She left her home, convinced that her parents would ask her to go back to school. She got a job in a record store and poured her energy into her punk rock band. She loved it. For a time, this new life was a necessary escape, but it presented its own challenges. The life of a musician was more chaotic somehow. It was, she found, too much about life, about emotions. The work sucks a lot of emotions out of you and requires always working with people. She began to look for a third option, something quieter and more stable. After a few years, Cheng got a little bit discouraged or bored with the music life. She decided to try university, but she faced an obvious hurdle. She hadn't graduated from high school. Turns out, her status of having qualified earlier to the special class for scientifically gifted children before she quit school became a savior. She could use this to gain admission to the university. She enrolled in the physics department at National Taiwan University. She planned to major in physics or math just to get into the university, and then switch to literature. She maintained what she described as a very on and off-again relationship with her studies, attending class only occasionally while continuing to play in her band and pursuing literature. The plan soon failed as she realized she is not good enough in literature. A single, very good class on quantum mechanics sparked a new realization for her. Attending that class was enough for her to find the subject actually pretty cool. She started paying a bit more attention to her physics and math studies. She started to find peace in it. Math and physics seemed to have this peaceful, quiet beauty, this space of serenity. After graduating in 2001, she decided to have one more year to study physics and see the world. She moved to the Netherlands. She earned her master's degree at Utrecht University under Nobel laureate Gerard Hooft. Working with Hooft was a big factor, she said. He was very open-minded and exposed her to many different questions in quantum gravity. Her PhD followed at the University of Amsterdam under Erik Verlinde, a world-renowned string theorist. When choosing a specialty, she followed the same motivation that brought her to physics in the first place. She got attracted by string theory because it's mathematically rigorous and pretty. Modern physics has a deep divide. Albert Einstein's general relativity perfectly describes large things like planets and galaxies. Quantum mechanics perfectly describes small things like atoms and particles. The problem is that the two theories contradict each other. Physicists have long searched for a theory of everything that unites them. One of the leading candidates is string theory. It proposes that if you zoom in on any particle, you will find it is not a point but a tiny, vibrating filament or string. Different vibrations of this one object create all the different particles we see, like different notes on a violin string. String theory posits that our universe must have 11 dimensions, far exceeding the 4 we experience, namely 3 of space and 1 of time. The 7 extra dimensions are theorized to be curled up and concealed within a minute geometric shape at every point in space. The specific geometry of these hidden dimensions is paramount, as it dictates the fundamental constants, the laws of physics, and the types of particles present in our universe. A major quest in physics is identifying this crucial shape. A K3 surface is a special 4-dimensional geometric object that serves as one of the most vital toy models for these structures. It offers a balance of simplicity for analysis and sufficient complexity to be meaningful. Miranda Cheng's PhD research focused on exploring black holes within string theories that incorporate K3 surfaces. In the 1970s, mathematician John Mackay noticed an unusual numerical coincidence. It was called moonshine because the idea seemed as outlandish as foolish or talking moonshine, a term the physicist Ernest Rutherford had once used to dismiss the idea of atomic energy. The mystery involved 2 completely separate parts of mathematics. To understand it, first, we must understand symmetry. A square has 8 symmetries, or ways you can turn or flip it so it looks the same. A group is the mathematical language for describing all the symmetries of an object. In the 1970s, mathematicians completed a huge project. They classified all the basic building blocks of symmetry. Most fit into neat families, but there were 26 exceptions. These were called the sporadic groups. The largest and strangest of all was the monster. It is a giant collection of symmetries, a structure of pure mathematics so large that the number of its elements is greater than the number of atoms in 1,000 Earths. The second clue came from number theory. It involved a special function called the J function. A function is like a machine. You put a number in and you get a number out. The J function was a famous modular form, a special kind of function with very powerful high-level symmetries. When expanded, the J function produces a specific sequence of numbers. The aha moment came when Mackay looked at the first number from the J function, 196, 884. He saw that it was the simple sum of the first 2 numbers that described the monster group, namely 1 and 196, 883. This could not be an accident. It meant that these 2 vast, unrelated fields, the study of symmetry groups and the study of modular forms, were secretly talking about the same thing. String theory proposes that all particles are just tiny, vibrating strings. This theory has 2 different geometries. The first geometry is the path the string makes as it moves. This path, called a world sheet, traces the shape of a donut, or torus. The mathematics of the J function describes this torus shape. The second geometry is the shape of the hidden dimensions that the string moves in. The mathematics of the monster group describes the symmetries of that shape. In 2010, a trio of physicists published a paper on a new, related moonshine. Cheng, with her deep background in K3 surfaces, read it and recognized the pattern. "It smells like another moonshine," she said. This new connection involved K3 surfaces. She and her collaborators, John Duncan and Jeffrey Harvey, began to investigate. They gradually teased out evidence of not one but 23 new moonshines. In 2012, Cheng, Duncan, and Harvey published their Umbral Moonshine conjecture. They proposed that these 23 new connections were not accidents. There were 23 new moonshines that connected 23 different symmetry groups to 23 different functions from number theory. They named it umbral from the Latin umbra, meaning shadow. The name was chosen because the functions involved were mock modular forms, a strange class of functions first studied by the mathematician Ramanujan. The conjecture's physical implication was its most powerful part. Cheng and her collaborators proposed that just as Monstrous moonshine was a footprint of a 24-dimensional string theory, their 23 new moonshines were footprints of 23 new special string theories. The scenery for all 23 of these new theories, they argued, was the K3 surface. Cheng's work suggested that the 23 moonshines were evidence of a hidden symmetry in K3 surfaces, a symmetry that no one had seen before. She had handed physicists a map, 23 times over, pointing them toward new, solvable toy models of quantum gravity. Mathematicians were electrified. In 2015, the conjecture's mathematical basis was proven by John Duncan, Michael Griffin, and Ken Ono. They confirmed that the 23 numerical connections were real. But the proof left a tantalizing puzzle, one that persists today. The proof was numerical. It did not build the physical string theories that would explain the connections. The proof is like looking for an animal on Mars and seeing its footprint, so we know it's there. We have the footprint. But we have not yet captured the animal. Cheng and other physicists are still on the trail of the K3 string theories that lie at the heart of the mystery. Her work on moonshine brought her wide recognition. In 2015, she received an ERC starting grant for her project, Moonshine and String Theory. In 2018, she was awarded a prestigious NWO VIDI grant worth €800,000, enabling her to build her own research group to continue the work. Lately, Dr. Cheng has been broadening her research to bundle together theoretical physics, mathematics, and artificial intelligence. Cheng is taking ideas from physics, like renormalization group flows, to look at and improve how AI systems, especially generative diffusion models, are put together. It is one of the largest personal grants in the Netherlands. Her journey overturns the cliches about child prodigies. She's a great example that mathematicians and scientists are just people doing math and science. They come in all shapes and sizes. The girl who couldn't deal with the competition in school never changed. She simply found a world without it.